Food. And what sort of food could I possibly want best? Kit Kat. But I'm going to put that aside for later. Today, I'm going to talk about raisin buns. Here we are, a little bun, mini bun, with raisins in it. How many raisins? You can just see the raisins at the end there. How many raisins do you think there might be in that bun? Well, one way to find out is to have a look. Oops, that one fell out. 1, 2, 3, 4, 5, 6, 7, 8. There are 10 raisins in that bun. So, these buns come in packs of 6 from 7-Eleven. And if I take another bun, how many raisins do you think there might be in that second bun? I think you'd be surprised if there were exactly 10. But I think you'd be surprised if it was a long way from 10. Let's just have a look and count the number in here. See? Look at that. And I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So one bun has 10, the other has 12. We're not going to expect them all to have exactly the same number of raisins. And these little buns come in packs of 6. So there are 6 buns. How many raisins would we expect to find in those 6 buns? Well, we had 10 in one, 12 in another. It could be that there are about, on average, 11 raisins per bun. So we would expect in 6 to have 66. And if we were to take 100 buns and work out the mean number of raisins per bun, then we might get 11, we might get 11.5. I don't know what the answer would be. I haven't actually done it. But if we did take 100 buns and work out the mean number of raisins per bun, and if it was around about 11, then if I took another 100 buns and worked out the mean number of raisins, I expect that that would be 11 or near enough. Again, the same sort of number. And so we could say quite reasonably, provided when they make the buns that they stir things up quite well and thoroughly and a proper mix, we could say that the number of buns, the mean number of raisins in a bun is constant, or that the raisins per bun occur at a constant rate. We say rate even though it's not time. If I only had 1 raisin in a bun, I'd complain. But if I had 20 raisins in a bun, I would think I was onto a good thing. Well, let's now take one of these buns and let's take a small piece. There we are, not very neatly done, but there is a small piece, and this piece has 3 raisins in it. Well, I could take a smaller piece, and a smaller piece, and a smaller piece, and a smaller piece, till I've taken a very, very tiny piece. The chances of finding a raisin in a really tiny piece, small, might be one still stuck to it, but the chances of finding 2 raisins in a tiny piece is so small that we can ignore it. And so we say that the raisins occur singly. You can take a smaller and smaller piece so that the chance of 1 raisin is small, and the chance of 2 raisins in a piece that size is so small that we can neglect it. This is what we mean when we say that raisins occur singly. As long as there's been a good mixing up of things when the buns were made and so on, then we could say that the raisins will occur independently and randomly. You've just seen an example of a Poisson distribution. The way that the raisins are distributed amongst the buns follows the conditions for a Poisson distribution. We can see that if we have a little look down here. As I mentioned in the video, the raisins occur at a constant rate, so that the mean number per bun, if we were to take a rather large number of buns, we would find that the mean was constant, perhaps 11. Then the mean number of raisins in a bag of 6 buns would be 6 times 11. So raisins occur at a constant rate. The second condition we need for a Poisson distribution is that raisins occur singly. This is what I showed you when we took a very small piece of bun, and the chances of getting 1 raisin in that piece was very small, and the probability of getting 2 raisins so small that we could ignore it. And then, provided that the mixture is all thoroughly mixed and there is no clagging together of raisins or anything like that, we can assume that the raisins occur independently and randomly. You're about to see another clip, this time of a Geiger counter. This is recording radiation near Chernobyl. Chernobyl was where there was a major nuclear accident in 1986, and it has been closed down, and the area around it closed down ever since. What I want you to notice is that the reading on the Geiger counter varies, but is never very far from somewhere around 125. In other words, we're looking at something where there is a constant mean. In the video, you could see that the radioactivity count at Chernobyl varied somewhat between about 118 and 136. If we were to take 2 separate 1-hour periods and work out the mean number of clicks per second in each of those hours, then I suspect you will get nearly the same answer in both cases. That is what we mean when we say that the clicks showing radiation occur at a constant rate. The second thing, clicks occur singly. This was like the raisins occurring singly in the previous example. We could take a very short time interval so that the probability of 1 click is very small, but so short that the probability of 2 clicks is so small that we could ignore it. That's another condition that we need for a Poisson distribution. Clicks must occur singly. Clicks also occur independently and randomly. One atom splitting up does not affect another one, and so they will be independent. Another example of a Poisson distribution could be patients arriving at a doctor's waiting room. This is perhaps not quite so good in some cases. Patients would arrive, if we're thinking of consulting hours, then it's possibly quite sensible to assume that patients arrive at a constant rate. This would be patients arriving without having made an appointment first. Patients arrive singly. I think that one's quite sensible. I think it's very unlikely that 2 patients will try and walk through the doorway side by side. So they will come in one at a time. Arrivals of patients, independent and random. Now that might not be the case. Possible that 2 patients from the same family might be ill at the same time, and there you've lost the independence. So this is something which might, under certain circumstances, be something we could say satisfied these conditions for the Poisson distribution, but we'd have to be a little bit careful with it. In general, we have a Poisson distribution if we have events which occur at a constant rate with a mean number of occurrences lambda in a fixed length of interval, if the events occur singly, and if the events occur independently and randomly. In this case, we write x twiddle p naught lambda. P naught for Poisson, lambda is the mean number of occurrences in an interval, where x is the number of events or occurrences in that interval, And the probability of R events in that interval is probability that x equals R is lambda to the R e to the minus lambda over R factorial. We can also use cumulative Poisson distribution tables in exactly the same way as we use the cumulative binomial distribution tables in the previous chapter. Now an example just to tie things together. Let's suppose that we have cars passing a particular point in the road at the rate of 5 cars per minute. Find the probability that exactly 4 cars pass the point in 1 minute. Well, here, if we take x to be the number of cars passing the point in 1 minute, then x twiddle p naught 5. That is an essential part of your solution. That is the method that we are using. We now want the probability that x equals 4. Well, remembering that the probability that x equals R is lambda to the R e to the minus lambda over R factorial. This will be lambda, which is 5, to the power of 4 e to the minus lambda, which is 5, divided by 4 factorial. That looks like 41 now. 4 factorial. And if we press the buttons on that, we get 0.175. 3 significant figures because I'm using my calculator. I could have used the cumulative tables. The probability that x equals 4 is the probability that x is less than or equal to 4. Take away the probability that x is less than or equal to 3. That is equal to 0.4405 minus 0.2650, and that is equal to 0.1755, 4 decimal places, because I'm using the tables. Okay, let's move on a little bit. Same problem, 5 cars per minute. Find the probability that at least 3, but fewer than 8, pass the point in 1 minute. So we still have x twiddle p naught 5. We want at least 3, so we're doing probability that x is at least 3. So it's got to be greater than or equal to 3. Let's put the 3 first. Less than or equal to x less than 8. That is the probability, this is just to emphasize it, that x is 3, 4, 5, 6, or 7, but not 8, which is the probability that x is less than or equal to 7, and take away the probability that x is less than or equal to 2. That gives me, looking up in the tables, the cumulative probability tables, 0.8666, and take away 0.1247, which is 0.7419, and I've given that to 4 decimal places because I've been using the tables. Let's look at a slightly different case. If I can move the thing upwards. It's moving now. Find the probability that more than 8 cars pass the point in 2 minutes. Now we had a mean of 5 cars in 1 minute. And as this is Poisson with a uniform rate, this means that the mean will be in 2 minutes will be 10 cars. So if y is the number passing the point in 2 minutes, that's a very nasty in, then y twiddle p naught 10. Once again, that is an important part of your solution. It is the method, it's how you're doing it. Well, if we've now got y twiddle p naught 10, we want the probability that y is more than 8. Y is more than 8, 1 minus the probability that y is less than or equal to 7. Looking in my tables, y is less than or equal to 8. More than 8, y less than or equal to 8. That is 1 minus 0.3328, and that is 0.6672 to 4 decimal places. Very similar in the way that we operate things to the binomial. It's just that if we are looking for a formula, the formula is different, and obviously the cumulative tables are going to give different numbers. Let's look at one more part. Find the probability that more than 3 cars pass the point in each of 2 separate minutes. So we are back to looking at 1 minute. In 1 minute, the mean is 5. And so we're looking at x twiddle p naught 5. In the first minute, the probability that x is more than 3 is 1 minus the probability that x is less than or equal to 3. That is 1 minus 0.2650, and that is 0.7350. Now, since the Poisson distribution insists that everything is independent, the cars passing the point are independent of each other, the second minute is going to have the same probability. And to find the probability that we get more than 3 in the first minute and more than 3 in the second minute, so the probability x is greater than 3 in the first minute and x is greater than 3 in the second minute is going to be the probability that x is greater than 3. I need a greater than 3 in the first minute times the probability that x is greater than 3 in the second minute. That's where we need the fact that everything is independent. This is just 0.7350 squared, and that is 0.540, and I give that to 3 significant figures because I've used my calculator.